All right, well, welcome everybody to still a very sunny day on the Jurassic coast. Not the Jurassic coast you might be familiar with on the south coast of England, but Chris and I made it up all the way to the far northeast of Scotland to look at the other Jurassic coast. So why would we come up all this way to look at Jurassic outcrops on the far northeast of Scotland? Well, this is a really interesting location because we're standing right along the margin of what's called the Inner Moray Firth Basin, which is the sea off to us here, which is genetically part of the North Sea Basin. So it's one of the few places in the UK that we can actually study rocks and outcrop that we find in the subsurface in the North Sea. So if you look behind me here, Chris, if you can kind of walk there, you can see the big hills behind us there. Well, there's a big fault that forms the boundary of those hills. And we are on the down-thrown side of a big normal fault. So the footwall side is the big hills over there, and we're on the down-thrown side here. And we're in the Upper Jurassic. So in the Upper Jurassic, these faults are actively moving, so we're looking at what is called Syn-Kinematic stratigraphy. The rocks were deposited at the same time as the fault was moving. So when we look at the Upper Jurassic stratigraphy here, you'll see some really interesting rock types. So when you get a little bit closer here, you can see that these are incredibly coarse-grained deposits. So we can see down below here is Upper Jurassic mudstone, same age as what ultimately becomes the source rock in the North Sea Basin. But above us here is a rock type where you can see very large clasts. You can see stratigraphy inside a clast here. There's another clast here, here and here. This is a debris flow deposit containing some very, very coarse-grained materials composed of Middle Jurassic and Devonian clasts that have been eroded off the footwall behind us. So these are debris flows that are coming out into the basin straight off the footwalls. In fact, if we stand back just a little bit, there is a quite impressive looking clast just behind us. Just over the hill, so you can see some stratigraphy dipping very steeply into the sea. And that is actually a bus-sized clast of Devonian material. So these are debris flows that are coming into the basin. And I try to make a little sketch of it here. Hopefully you can kind of see what I try to draw here. But this is the bounding fault that sits behind us. And then there's probably very shallow water hinterland in the Upper Jurassic, and coming off the fault are these debris flows which make these tongue-shaped deposits out into the basin. Stacks of these on seismic data typically look very chaotic in seismic reflectivity. They're very high impedance. It's a very typical seismic phases, and there's a term for that called MTC. Most of these, even though they have some very coarse-grained materials in there, these are really non-reservoirs because they are mud supported. Now what's interesting here, if you look further over behind me there towards the south, you can see a lot of other stratigraphy, everything gently dipping into the sea. There's actually a lot of small lobe deposits, turbidites, so some coarser and medium grained sands, pretty good reservoir quality. But they're actually not coming straight off the mountains behind us. But if you look at paleocurrent direction, they're actually coming obliquely towards us. So they're coming from a point further to the south. So what's kind of interesting in this setting, in this sort of Syn-Kinematic setting, is that you get that interaction of debris flow deposits with more higher quality turbidite deposits that are traveling in a more axial part into the basin. So they're not genetically related, although sometimes you see people drawing cartoons where the debris flows sit up dip of these, but obviously they interact with each other significantly. So out in here you can see the resistant bed sands. It's about 20 to 40% net to gross out there. So it's not terrible, but obviously it's part of another depositional system. So what we'll do in the next outcrop, we're going to try to find where this depositional system gets much higher net to gross and talk a little bit about why that is there. So let's move on to the next outcrop. All right, well, we've come a few kilometers south from where we were in the last outcrop. We're in about the same stratigraphic interval, and again we're about a kilometer removed from the bounding fault. So we're again in the hanging wall, looking at Upper Jurassic marine deposits. Now obviously it looks quite a little bit different here compared to the last outcrop. For one, as we look around the wave cut platform, there really aren't any boulder beds or debris flow deposits preserved here. It's actually a really high net to gross sandy system, probably about 80% net to gross. And then you get these nice exposures here of the sandstone. So they're a few meters high, and the sandstones here are typically medium to coarse grained, very well sorted, and they look a little bit like a mess. So to the untrained eye, these can be quite difficult outcrops, but there's a few things we can decipher from here to kind of get the picture. First thing you have to kind of wrap your head around is these really high angle steep surfaces that cut through here. Those are actually deformation bands, so they're a much later tectonic feature in these sandstones that you kind of have to almost imagine they're not there if you want to figure out the depositional part of it. But then when you look carefully in here, you'll do actually see a few interesting features. You'll see a lot of scour surfaces in here. So you can see here the base of the sand is cutting down into the underlying sand. So there's a lot of scour surfaces in here. And there's a lot of low angle dipping surfaces running through here at a little bit of an angle, such as the one over here, to the overall bedding geometry. So they're dipping into there. Those are basically large scale bed forms that are forming from turbulent flows. What's really interesting, you'll see a lot of places where those surfaces have got these little kind of chipped appearances in here. So that's where there used to be larger clasts inside of there that have been ripped out. Now it's really interesting here, when you dig into here, and I've picked out a piece here, the clasts here are actually, they're not pebbles, but they're actually things like this. So this is the base of the bed here. So these are all little shale rip-up clasts that are in there. So what's happening here is the flows, these sandy flows that are ripping up, the turbulent flows, the eddies are ripping up the underlying clay that's in the Kimmeridge clay formation. So you get this pattern of very high net to gross, very well sorted, coarse to medium sands, with these rip-up clasts and these low angle dipping surfaces that are forming long wavelength bed forms in here. If you see that in the core, that's kind of a very typical motif, and it really, even with the poor outcrop quality, puts you in a very specific part of the depositional system. Part of the reason you don't see much structure in here is because most of these beds have been completely fluidized, so we're dealing here with very rapid deposition. So where are we in a depositional system? Well, we can always argue and interpret this, but I would argue that the most likely spot that we are here are right at the transition of a channel to a lobe. Okay, so what happens in that channel lobe transition into this proximal part of lobe is, as the flow decelerates, it just drops out all of its coarser grained materials that are being transported by traction, in this case medium to coarse grained sand. So if you see really high net to gross, well sorted sands with these shale rip up clasts in there, at a high net to gross, in this case about 80%, you are probably very close to the input feeder, the channelized input feeder of the system. So this is a schematic diagram of what this depositional system might look like, and we can use terms like proximal, medial and distal to discern the locations that we're at in that lobe system, typically related to net to gross. And using that, we can go back to the outcrop we were this morning and say, well, if we take away those debris flow deposits that's coming off the margin, looking at the system that comes in a little bit more axially, we'd probably be in a more distal position on that lobe complex. So that's really the story of this outcrop. We've kind of moved into the more proximal part of this depositional system, much higher net to gross, which obviously is where you want to be for your reservoir. And now the key question is, well, why here? Why is the high net to gross here? When you're exploring for these things, particularly in these systems that are syn-tectonic to the fold movement, there are some very specific places where we get the best reservoir developed. And we'll give you the final piece in the puzzle in the last outcrop that we'll look at to kind of sum up this whole Syn-Kinematic deep water depositional system. All right, so the last couple of outcrops, we were over by the coast looking at Upper Jurassic sediment gravity flow deposits in deep water. So now we've come inland a bit, so kind of standing on kind of slightly elevated terrain. So why would we come here? Well, where we're standing right now would be the footwall of one of the bounding faults of this syn-tectonic depositional system. So back in the Upper Jurassic, imagine that we'd be in shallow water settings here. And what's really interesting is that you'll see quite a big gorge coming in here and going into the mountains. So there's a present-day river coming through, and as you trace it down towards the coast, you just follow the yellow gorse. That's where the river goes underneath a railroad bridge, and just as you come out of there, that's the second outcrop that we looked at today, with the very high net to gross sands in a channel lobe transition to proximal lobe complex. So what's really interesting is that we're standing on the footwall of the fault here, but where the river is, there's actually a segment in the fault. So the fault is segmented, and actually on the other side steps quite far back. So that fault segmentation is actually causing the river to follow this present day pattern. And you can imagine that back in the Upper Jurassic, it probably wasn't all that dissimilar in terms of finding that entry point. So one of the keys here is that notion of what we call relay ramp. So here's a little bit of a drawing of kind of everything that we've looked at today. And we are standing roughly about here on the dipping part of this fault segment, and then the other fault segment is back over there, stepping back a bit. And what happens is that the footwall of the block we're standing on here has to connect into the hanging wall of the next fault, and it does that by very, very steep dips, even in the present day. So that's what we call a relay ramp. It's a really good point to focus sediment delivery into a basin. And in this case, our second outcrop will be down dip of this relay ramp in a more proximal part, so very high sand content. And as it traverses and it actually bends back in the Upper Jurassic, we get into a Port Gower outcrop, which is in a more distal part of that depositional system, but also punctuated by these debris flows that are coming off. So the debris flow deposits and these turbidites are interacting with each other, but they're very distinct depositional systems. What is really cool about this configuration is that you can see I've kind of drawn a little bit of an anticlinal shape here, because as this fault segment subsides and this one subsides, it actually causes a structuring right where the main reservoirs are coming in. So it's a perfect place of finding a combination of very subtle traps and also very well developed reservoirs. So when you're dealing with your seismic data and you're dealing with these syn-tectonic depositional systems, a really good place to hunt for prospects is finding these segments in the relays and looking for where you see that subtle depositional thickening of your syn-tectonic strata, and it might be under closure. The only thing you have to do is try to figure out how to seal it up dip. We'll leave that for another lecture. So hopefully that kind of ties all these outcrops together. What parts of the world is this relevant for? Well, anywhere where you work in either very steep slopes, where you see interactions with debris flows and turbidites, and when you're dealing with syn-tectonic systems. So if you're working Suriname, Guyana, this is something to think about. If you're working of the West Africa, Brazil, the early post-rift basins, the Cretaceous stuff, you'll see a lot of these motifs. And you'll actually see some of these motifs in mini basins associated with mobile substrates that's moving around, such as salt basins like Gulf of Mexico or shale basins like the Niger Delta. So in short, relevant for almost probably any of you working on these types of systems. So hopefully that was a useful kind of compilation of a few outcrops here in the Upper Jurassic of Northeast Scotland, and hopefully you got a bit of an idea of why Chris and I decided to come out all this way.